Welcome everybody. Today presentation is by E.Halubek. He's accomplishing his engineering degree at Łódź University of Technology, and he is also working at Institute of Physics Polish Academy of Science. And today's presentation is fabrication of the fastest thermometers in the world. Welcome, Eric. Please go ahead.
Hello, everybody. Thank you for introduction. So I would like to tell you about what I'm doing right now as I'm trying to finish my engineering thesis. I'm a bachelor student of physics engineering in Poland. So I'm focused now on fabricating nanostructures, the fastest nanothermometers that are currently known in CoolPhone group, which is a group, a scientific group in Institute of Physics in Warsaw of Polish Academy of Science, where we are mostly focused on these nanothermometers, but also some other nano devices. And in our group, there are 5 people, including me. So when we want to talk about a thermometer, we should start with a heat flow problem. So let's consider such generic problem of some body with heat capacity CV that is kept at elevated temperature um, um, above the reservoir, but it is connected to the reservoir with a thermal link with thermal conductance GTH that makes the heat flow possible. So the power of that heat transfer is equal to the thermal conductance multiplied by the temperature difference between the reservoir and that body. And also, if we consider the internal energy that is stored in the body with heat capacity CV, we get to the conclusion that it can be expressed in a linear regime. It can be expressed approximately as that heat capacity multiplied by a difference of temperature between the body and the reservoir. And of course, the heat capacity at the temperature T0 at which the reservoir is kept. And then if we um, and if we take the derivative with respect to time of that energy that is stored in that body, we get such equation, which when we solve it gives us exponential decay of the temperature difference between the body and the reservoir. And the relaxation times of this body of heat capacity CV in our cases can be as low as 10 nanoseconds. So obviously it's dependent on the size of the body. The smaller the body, um, the the lower the relaxation time would be. And so in our nanothermometers, we can measure such uh, rapid changes in temperature that happen in a nanosecond regime. But before diving deeper into what these thermometers are, let's say something about superconductivity, because these are superconducting structures that we use. So, superconductivity was discovered in year 1911 by physicist Caroline Nones, when he was measuring the resistance of a sample of mercury at the temperature near the boiling point of liquid helium. And he also was the first in history to liquefy helium. So that's one of the reasons why he achieved superconductivity as
By the
the
way,
first person in
Eric,
the world.
By
Yes.
the way, he bought cooling devices from Jagiellonian University. Jagiellonian University produced cooling apparatus for liquid nitrogen and
Yeah, I
oxygen.
know. Yeah.
And
Yeah.
then, so this equipment was improved by Carl Ones in such a way that he managed to get, liquid helium. But it's also important to mention this contribution of some Polish people from Jagiellonian University as well. Thank you. Mhm.
Yes, yeah, that's true. So now we know that the critical temperature, which is the temperature at which the mercury uh, changes from a normal state to that state of no resistance, is a little bit lower than 4.2 K. It's about 4 point, um, it's about 4.15 something like that. It's slightly lower. So Caroline Gonis noticed that weird phenomena of superconductivity, and then 50 years later, um, in year 1957, Bardeen, Cooper, and Schreiber showed us the theory of superconductivity, which explained the superconducting state as observed in metals. And the mechanism of superconductivity, as explained by this theory, was that electrons pair can pair into what's called a Cooper pair, and they move through the crystal lattice in such pairs without dissipating energy, and without um, without losing that energy by interactions with a lattice.
Eric, I have a question.
Yeah.
So those two electrons, when they create a pair, they become a kind of different particle than fermions. They become a bosons. What this is about?
So when they pair, they are not technically a boson, but we can consider them as something that is like a quasi boson. It's not it such a pair has integer spin then. So
Yeah.
well,
So
yes.
this
So
my suggest this they are subjected to Bose-Einstein statistics, right? Which
exactly. So
which can
yes,
also mean that there is higher critical current density as it is being observed in superconductors. So in a way, we can recognize this process as first stage of Bose-Einstein condensation at some point, right? This
yeah.
mechanism of pairing of electrons. Okay, thank you. Mhm.
So um, the Aharonov-Bohm effect is somehow related also with what we are doing in our lab, because these thermometers are specific kind of structures that utilize this effect. And so what is it all about? It's that some particle, if we have a particle of some charge q, then the wave function of that particle acquires phase due to a vector potential that is in the space through which this particle passes. So the phase difference in a superconducting circuit across a weak link, which is uh, a place in the superconductor where superconductivity is weakened due to its size. That it's just a constriction in the structure, and the phase difference that appears there is given by such equation, and this leads us to the Josephson effect. And so in Josephson effect, Cooper pairs can tunnel through a barrier that can be um, an oxide layer, or as I said, weak link, a place in the superconductor where superconductivity is weakened um, due to this constriction in the superconductor. If we imagined um, blue piece of a superconductor here instead of this red barrier, but just in form of a constriction, that would be a weak link, Josephson junction, and also there's another type of Josephson junction where this barrier is just an aluminum oxide layer. This is the tunnel junction. So through this kind of structure, we observe that there can be uh, a current flowing across it that is proportional to the sign of phase difference on the sides of this junction. So on the left side of the junction, we have some phase theta one of a condensate of these Cooper pairs that, as we said, they can be treated like bosons. So they can condense into a single quantum state with a common phase, and the same is true on the right side when we have some different value of that phase, and that allows the current to flow through that superconductor. And so
Oh,
we can apply some voltage to such kind of junction,
I see.
with Josephson effect, where the difference of the phases is then dependent of time, and the value of current is fluctuating in time, and the DC Josephson effect when there's no voltage and the value of the current is constant in time.
Right. So in a
Yeah.
sense, this can you come back to the previous slide? Yeah. So what is essential for the whole system that showing Josephson effect is this the fact that there's macroscopic wave function, right? So in a sense, macroscopic wave function is continuous across the whole system, right? You can then associate phase to left and right reservoir, right? So
Yeah.
that's quite essential assumption from your side, right?
True. Yeah.
All right, please go ahead.
Okay. So our nanothermometer is constriction in in the superconductor. In this case, this is aluminum sample, and this image is taken under scanning electron microscope, where we can see that the constriction is 60 nanometers. It's usually in this kind of range, about from 60 to 70 nanometers. And so in this kind of junction, there is, to be precise, there's no tunneling of the Cooper pairs, but that there is still that current current that was that, that I said that was present in the Josephson due to the Josephson effect, because there is a phase difference of the wave functions on the left side and the right side, but there's no like a precise point at which the phase changes from one value to another. There's more like a gradient of that phase. It's more smooth change through that junction.
What you are showing is Diamond bridge, right? This is Diamond bridge. It's a weakling
Yes,
of
this is
Josephson
also
junction.
called. Yes, this is also called dime nanobridge. Yeah,
Yeah. So, by the way, what's critical temperature of aluminum?
it depends on your grain size. That you can see here, the grains are pretty small.
Yeah.
In this case, it is around 1.3 Kelvin.
So you
It
have
really
measured
depends.
by. So you have experience with this material, right? You already measured aluminum superconducting properties, right?
Yes, we were measuring these samples, but
Mm-hmm.
and I have not prepared them myself, because now I'm preparing titanium samples by myself. So
Mm-hmm.
yes, I was present during the measurements. I can say.
All right. Mm-hmm. I do.
So yes. So what these dime nanobridges, these nanothermometers can be used is to detect the vortex expulsion from such structure. So superconductors have such property that they don't want to be penetrated by a magnetic field. And in some cases, this leads to um, complete expulsion of the magnetic field from the superconductor when there's no penetration at all. But in some cases, which in materials which we call type 2 superconductors, there can be a penetration of that superconductor by magnetic field, and that leads us um, to 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 the phenomenon that we call the superconducting vortex, where we have a vortex like a tornado, where the current is flowing around the center of that vortex, and the value of flux that is generated by such thing is equal to flux quantum, which is the smallest value of the magnetic flux that is possible. It's Planck constant divided by 2 times the electric charge of the elementary charge. So in our group there is some kind of idea that this can be used as a quantum computer memory cell, and this is what got me interested in these studies. This is the reason why one of the reasons why I joined this group, because they recently published this super interesting article where they were showing that it is possible to control the movement of that vortex by sending current pulses through a nanowire, and then when the vortex is expelled from the box, we observe that it generates quasi-particles, which are electrons in this case, because naturally free electrons are not observed in a superconductor, so that's why we call them quasi-particles. And these quasi-particles then lead to mm, heating of the structure, which is observed by the nanothermometer by this dime nanobridge. That's how we know that the
Yeah.
vortex
So
is extant.
Eric, so So since quasi-particles are not paired, to which statistics they are subjected?
Yeah, the
If
Fermi-Dirac statistics. Yeah.
which is also responsible for Ohm law in so which is
Yeah.
responsible for dissipation of energy. So in a sense, the quasi-particle movement, right, will be responsible for voltage generation we observe, right?
Yes. Yes.
Right.
Yeah.
Go ahead, Eric.
Yes. So when the vortex is present in the nanostructure, because it appears by itself at the proper value of a magnetic field, which is applied to the structure, it just enters it from in most cases from some kind of corner, um, such sharp places, and it just stays there as long as there's no current pulse. And this can be thought of as state which we assign one to the state, and when we send the current pulse through the structure, then we expel the vortex, and where there's no vortex, the state can be, we can assign zero to this state. So that can be thought of as some kind of memory cell. So let's say something about how we know that a certain temperature is observed at a certain point of space and time by the nanothermometers. Uh, so how we measure our temperature is that we apply some number of rectangular current pulses, and then we record switchings and some other number of switchings of this nanothermometer to a normal state from the superconducting state. So we measure the voltage drop across the junction, because when there's a superconducting state, there's no voltage across the junction. And when it switches to normal state, there obviously is some kind of voltage. And so then if we repeat this process, we send many pulses and register many switchings, then we can estimate the probability of the switching by dividing the number of switchings by the number of pulses that were applied to the structure. And this allows us to assign some value of current, some current amplitude uh, to that to some kind of temperature uh, in at which the switching is taking place, when the probability of switching is 50%. So in case where we increase the amplitude of the current pulses that are applied, the probability of switching increases also at a certain temperature. But when we lower the value of the amplitude of this current pulses, the probability of switching the thermometer also decreases at a certain constant temperature. So that's how we calibrate our thermometer. And there's a slightly different approach to measuring fast um, fast changes of temperature. But now I wanted to just give you an idea of how this probability of switching is related to a temperature. So here are the calibration curves of an aluminum nanothermometer, where you can see that at a high temperature, which is let's say 800 millikelvin, then the switching current is around, let's say, 40 microamps. So the current at which the probability of switching is 50%. when we count around 5,000 switchings for 10,000 pulses sent. But as we drop the temperature to around let's say the 400 millikelvin, it could go lower because technically this aluminum nanothermometer could be calibrated down to 250 millikelvin, but that's what we have here on this chart. So let's say 400 and 57, let's say 57, 50 something, 57 something microamperes for the probability, for the same 50% probability. So as the current increases, then the probability of switching at a certain constant temperature increases. And as the temperature drops, then we know that also this the temperature of the surrounding of the thermometer at which it is kept, that also corresponds to a higher value of the switching current. So that's an idea of how you can measure the temperature by such junction. And the limiting factor here in in this method is the duration of the pulse that you send uh, through your structure. So it's a limitation due to the capabilities of your generator. Okay, and I wanted to talk especially about the sample preparation because that's what I'm doing right now, like all the time practically. So the first step in sample preparation is to take such silicon wafer and dice it into squares, small squares that are approximately 10 millimeters um, of side length, around 10 millimeters. Then we place these tiny squares into acetone. We put it into ultrasonic cleaning at 80 kilohertz for 2 minutes at 30 degrees to remove all kinds of debris and things that are attached to the silicon that we don't want them to be. Then we take it out of the acetone bath while rinsing with isopropanol. And it's important because acetone evaporates much quicker than isopropanol, and it leaves um, all kinds of impurities that were dissolved into it on the surface of our substrate. Um, so if we rinse it with isopropanol before taking it out of the bath, that prevents these these impurities from from um, from forming from crystallizing out of the acetone. And the last step is to dry it with pure nitrogen. Is the same class of nitrogen that is used um, for food. So it is very clean. Uh, and it cannot have any kinds of oils or grease remainings that are often present in um, lower purity nitrogen. And the next step is to um, coat your sample with resist. So before applying resist, onto our square. You can see here in this figure. Um, we um, we usually additionally clean it with isopropanol by spinning it on the on the um, on our spinner and at around 5,000 um, RPM, and then we apply 3 drops of PMMA 950K resist.
RPM stands rotations per minute, right? RPM, right?
Yes, rotations
Abbreviation.
per minute. Yeah,
Okay.
yeah, yes. So PMMA 950K is pretty common uh, kind of resist that is used here.
Can you elaborate
Um,
what is PMA abbreviation for? Stands for
so
PMMA.
I think you know plexiglass, what plexiglass is. Yes,
All right.
the kind of the it's a kind of polymer that is transparent and is used
Yeah.
in yeah it's used in many in many
I
things.
see.
I think we,
Okay.
we, we all we all know what is plexiglass, so this is just an abbreviation for that.
All right. Thanks.
And that 950K is just a type of that material that tells you about the molecular mass of it. So after applying this substance, which is dissolved in anisole, uh, we spin it at 6,000 rotations per minute for about a minute to form 200 nanometer, around 200 nanometers of uh, of that of the layer. Then the last step is to heat it in 170 degrees Celsius for about 15 minutes to get rid of all the anisole remaining that was used to dissolve this PMMA. So the next step is mask patterning when we use a beam of electrons. These electrons are accelerated to very high speeds by a potential difference of around 30 kilovolts, and they can reach 100,000 kilometers per second. And then when such an electron um, is um, is colliding with the particles of the resist, it breaks them, and it makes these particles more susceptible to um, our chemicals that are used in the next step to remove what we don't want. So what you see in this figure is our sample. This is my sample that I made. It is placed on the holder which we put into this electron microscope. We use size neon or Auriga uh, 40 microscope. Um, and here's the layout of the structures. So each box from 1 to 5 is one structure when we have 2 contact pads that you will see on the next slide, and in the middle there's a nanostructure with what will be uh, um, what will become a nanothermometer. There's just a pattern of that. Okay, so next step is mass development. So this what we want to make is called a mask, um, because it masks it masks what we have underneath the silicon. So this image is an image from optical microscope of a mask after development. And the idea of this development is that when you apply special chemicals to the layer of uh, of the resist that was exposed to beam of electrons, then these places which were exposed are removed easier and quicker than the places which were intact, which were not exposed to electrons. And that allows us to get a pattern that we want. So this green, uh, this green area is the resist that we have, and the red area is the the part of the resist that will be removed due to a chemical reaction. And after that, we get something that we can see here, a mask, which can be then used to deposit metal that we want.
Okay, can you
Just,
come back to previous slide for a
yeah.
second?
Okay.
This this abbreviation MIBK, can you
Yes, this
stands
is
for
methyl isobutyl ketone. It's a name of chemical compound.
which is the red one?
The red
Which
one,
color?
okay. The red
It's
one
resist,
is
right?
the
It's
mix.
resist.
Yes, the red one is the mix. You can think of it as the mix of this chemical compound and isopropanol, but I wanted to show that these are the places which are removed due to the interaction of
Yeah.
these
But okay,
chemicals with resins. Yeah,
the the black one is
it is silicon
which
substrate. The black one is
silicon
silicon substrate.
substrate. Okay,
Yeah,
silicon substrate. I understand. Semiconductor. Okay, the green one is
this is resist. This will remain after the development. The green
okay,
part will remain.
and the red one is
And the red one is the part which is removed in the process.
yeah. So what's the chemical compound? What's the difference between red and the green? What are the compounds involved in that structures?
Yeah, so as I said, the red one, the places which are red are the places where you have the compound, the same compound as green, but the, it is shattered by a beam of
Okay,
electrons. The bonds are broken
okay,
in some
okay.
places in these particles, so the polymer chain is shorter, and it's easier to remove. And these places
All
will
right.
be
So
removed.
okay, now I get it. Now I get it. Now I get it. Yeah. So in a sense, the red one is the place of matter resist exposed to this beam of electrons, where polymer chain is affected and partly destroyed. Right. That's what you are
Yes,
saying.
but this is important also that this place where you see red area was not exposed to a beam of electrons, but it is also slightly affected by this chemical, but not as much as the place where there was exposure to electron. Okay, there's just few nanometers, let's say, that is removed to this due to this interaction. But where in places where there was exposure to electron beam, everything is removed. Okay.
Yeah, I see. All right. Okay. Thanks for explanation.
Okay.
Please go ahead.
So the next step is to deposit the metal. It is done in such high vacuum chamber this chamber is called by us Crazy Roger because of all the crazy things that it made us do. And so in such chamber, there are vacuums um, in range of 10 to minus 8 to 10 minus 11 millibar. So these are really high vacuums. And to achieve such vacuums, first you need to pump it with a normal vacuum pump to, let's say, 10 to minus 2 millibars, and then you use turbomolecular pumps that are present here. This little one is used for the load lock. This this thing that kind of resembles a gun in some way. When you put your sample, when you place your sample um, to transfer it to the main chamber. So first you put your sample there to the load lock, and then you remove the air from the load lock. And after that, you can open the gate, which is connected, which is a connecting element of the chamber that connects the chamber to the load lock. And then here you can move your sample to the main chamber. And main chamber has its own vacuum pump, the turbomolecular pump, slightly bigger here. And these pumps are um, really crazy because they they rotate at speeds. The rotational speed is like 1,000 rotations per second. So that's really fast. And the idea is that the speed of rotation of the blades has to be in range of the speed of the particles due to the due to their temperature to remove them. So when everything is placed, when your sample is placed in the chamber, you can see it through this window, and then you can start heating the uh, crucible of metal, which is placed at the bottom of the chamber. There are few possibilities to choose from because there is titanium crucible, aluminum, gold, and something else, but I don't remember. And then when you choose your crucible that you want to use, which metal you want to evaporate, you apply um, you apply a beam of electrons to it, which heats it, and then the atoms of that metal um, are um, are moving from the bottom to your sample um, through the vacuum and are depositing on your sample. So what is happening is that the layer of your metal is appearing on the top of the mask that we made in the previous step, and also um, on the places where it has almost direct contact with the substrate. Technically, there is really thin layer of a silicon oxide that is present in our case because we have not cleaned it with HF, that is used that I know that is used when you're making superconducting qubits that prevents from many many phenomena that are not wanted in such circuits. But here we don't really need it, and yeah, and HF is also pretty toxic. So um, when the metal is deposited, you can do the lift.
Okay,
So
can you,
now
so this black one is substrate, right? The black,
the black
the
one
black,
is substrate, is silicon
okay,
substrate.
and the green one
Resist.
is
This
resist,
is
okay?
resist. Yeah.
Okay. How long it takes to, can you come back? Um, so this evaporation metals in high vacuum, how long this process takes in hours or minutes?
So it depends on the rate that you are using because you can evaporate with a very low rate, like zero point 0.2 angstroms per second. And if you want to um, have, let's say, 30 or 14 nanometers of your metal, it takes like half an hour because in between the sessions of evaporation, you make a break. It's like you open what's called the shutter, uh, and it exposes your sample to the beam of atoms that is coming from this crucible. For some time, you evaporate some of some part of the layer, let's say 5 nanometers. Then you close this shutter, so now you stop evaporating. You stop applying new new atoms onto what you already have. But this crucible is constantly heated, so um, the layer is forming everywhere inside of the chamber, except for your sample because um, it's this shutter is closed. So yeah. So yeah, when you apply these 5 nanometers and you want to continue, then you open the shutter and you let the atoms flow again. It's one of the techniques that is used because it may prevent the resist from overheating. It is not necessarily um, needed if you have a resist that is compatible with high temperatures, but in our case, we use it. So that's when you have a really low rate of evaporating, um, it can take a lot of time. But with titanium, it is recommended to use rather higher values of evaporation rates, around 1 nanometer per second, because titanium is really reactive. And even if you have really good vacuum, that is, let's say, 10 to minus 10 millibar, then even then, that some remaining oxygen that is present in the chamber can interact with titanium and form oxide layers. And when these layers form, they form in full volume of your sample. So it makes it behave in a weird way like a semiconductor when you cool it, its resistance is rising instead of dropping. But if your rate is right, so you have to know such a trivial parameter as how quick you want to uh, put your layer onto the sample is really important. But when you do it with a right rate, you can make a great sample. But if you do it with the in case of titanium with a really low rate, it changes everything and makes your sample non-conductive. So when when this uh, when this evaporation is done, then it's time to lift off. When you when you apply acetone, heated acetone, uh, which removes the resist. So as you can see in this figure, places where acetone has contact with resist, it it eats the resist, it removes it, but when acetone is applied on the surface of the metal film, it does nothing to it. It just stays there. The metal film, which is connected nearly directly to the black thing, the substrate, it stays there. This green part will be removed with the metal that was deposited onto it in form of flakes. It looks really cool when you have it in a beaker. And these are just like flakes, like snow, like you have snowballs. Instead of snow, you have flakes of titanium that are uh, 20 or 30 nanometers thick. It looks interesting. So when it's done, you can enjoy your nanostructure. And here are all the steps that that are um, that were described. Before that, um, let's say before making all these steps, you can think um, of the of the specific um, needs that are required um, for material that you want to evaporate because, as I said, titanium, for example, is really problematic right now, especially as I'm doing these samples, where the aluminum was much easier to handle because titanium has much higher reactivity than aluminum and higher melting point. And
By the
this
way,
causes, yeah.
what's the critical temperature? What's critical superconducting temperature of titanium and aluminum? Just could you refresh our knowledge on that topic?
Yes, I wanted to say something about it on the last slide, okay? That there will
Okay.
be some kind of comparison. Okay. And here's a close-up view of the structure that I made. This is the titanium that was evaporated. And here's an image taken under the scanning electron microscope. So the piece of metal that is here on the left side is one contact pad. The piece of metal on the right side is the right contact pad. And here are the lines that that deliver the um, the current pulses to nanowire and then that nano thermometer that is really small. If we magnify it more, we can start we can start to seeing it. Um, and if I magnify it even more, then here it is. And in this case, the um, the width of that bridge is 80 nanometers, and it's about 180 nanometers long. So this is this quick link. Okay. So um, you wanted to wanted me to say something about the critical temperature. So the critical temperature of titanium is highly dependent on how you prepare your um, film, because it depends on the rate at which you evaporate it. It depends on the level of vacuum that you had in your vacuum chamber, because of the impurities that could be involved in the process of forming oxides. But it is it could range from let's say 200 millikelvin up to 600 millikelvin. It really depends on how you prepared your sample. With aluminum, it is about 1.3 Kelvin, and aluminum is not as demanding. But the reason why we are trying to use titanium, I am making these titanium samples, is that we want our thermometer to be useful in lower temperatures than this 250 milliK calibration limit for aluminum-based thermometers. And we think that may be possible because of theoretically lower value of critical temperature of titanium. But it is yet to be seen. We have not measured a titanium-made nanothermometer yet, because now we have trouble with oxidization uh, of these structures, and we are trying to tackle this problem now by um, making our vacuum better. We want to go as low as 10 to minus 11 millibar, and we will try to evaporate it with higher rate, around 2 angstroms per second, because previously we used zero point 0.4 angstroms per second, which according to literature is a little bit too low, and allows the oxide to form really quickly, which then results in this suspicious um, phenomena that we observed of increasing resistivity as we cool our sample. So that's it from me. Thank you for your attention.